sticking around so late. I appreciate you're all very tired. I definitely know I am. And thank you very much as well for allowing me to move my talk. It's been brought forward by 40 minutes, so if you're not here for this talk, then please do ignore me or audibly sigh if it gets a bit too boring. But hopefully, if you're interested in antibodies or graph neural networks, then at least some of this should be kind of interesting. So I appreciate that not everyone actually comes from an antibody background, so I thought it'd be useful to just have a quick overview. So I'm sure that all of you have seen the picture on the left-hand side, classic Y-shaped antibody made up of 4 chains, the heavy chain shown in gray, and the light chains, which are shown in white. And the bit that we're interested of the antibody is on the end of the arm. So the entire arm of the antibody, I might refer to as the Fab. The kind of forearm of the antibody is the Fv region. And on the end of the antibody, you've got 6 loops, which are the CDR loops. And that's where the majority of binding residues are most often found. So now we're kind of on the same page of what an antibody is. One last thing as well. Antibodies do bind with very high specificity. So this is an assumption that we've made in our work. So we're assuming that the paratope of an antibody is fixed, as in it will always bind the same target, or if it's broadly neutralizing, then it will always bind similar epitopes. So the paratope won't change. So why do we actually care about predicting the paratope? So there are a couple of main reasons. The first is antibody design, which can be kind of split into different parts. So one reason might be if we're trying to improve the affinity of antibody binding. And if we're doing that, then we want to be mutating the residues that actually form contact with the antigen. So in that case, we want to mutate the paratope residues. However, if we want to kind of change other properties about the antibody without affecting the binding, such as to improve stability, then we might want to leave the paratope alone. And if we're making a load of mutations, then maybe we want to know if all of these mutations have actually caused the paratope to just completely shift, and the kind of binding properties of the antibody are just now completely different. So that's kind of one reason. The other reason would be computational docking, which is where you would take a structure of an antibody and a structure of an antigen in silico, and you try to hit them together in certain ways to try and minimize the energy and try to kind of recapitulate the true binding conformation there. The issue is that proteins aren't as simple as the jigsaw pieces, and there's loads and loads of orientations that these things can be in. So it's a huge kind of combinatorial problem. And knowledge of the paratope and knowledge of the epitope, the binding site on the antigen, could really reduce the search space. And it wouldn't be quite like that, but we'd be able to reduce it so that we would have hopefully a much smaller, possibly searchable search space, and we're more likely to get the accurate complex out the other end, and to do so faster than current methods allow. So now that we've seen kind of what an antibody is and why we care about it, then we can get into the tool that I've been working on, which is called Paragraph. So this is a very high-level overview of the Paragraph architecture. And the first thing that I want to point out is that Paragraph is trained on both crystal and model structures. So our crystal structures come from our structural antibody database, SABDAB. And I think that Seb mentioned earlier that the PDB has 200,000 complexes. So we scrape that for all of the antibody and nanobody structures. We've got about 6,000 structures in there. And we've got about just over 1,000 high-quality, non-redundant structures to train on. We also train on model structures of those same antibodies. And the reason for doing that is that we really need our predictions to work well on model structures, because we're very unlikely to have the crystal structures in real life. They're very costly and time expensive to obtain. And if we do have the crystal structures, it's very likely to actually be in contact with the antigen. So we don't need to predict the paratope in those instances. So what we do is we take the PDB files of these crystal and model structures. We create a really simple graph representation. So what we do is we represent every residue in the antibody of the area that we're interested in as a node. So we've got one node is one residue. The coordinates of those nodes are given by the C alpha coordinates in the crystal or model structures. And associated with each node is a 22-dimensional feature vector, which is a simple one-hot encoding of the amino acid type and a one-hot encoding of the chain ID. So is that the heavy chain or the light chain? And that's it. That's our really simple graph representation. And what we do is we feed that into a series of 6 equivariant graph neural network layers, which are quite recent, but really popular at the moment. And if you haven't come across equivariance before, it basically means that it doesn't matter what orientation the crystal or model structure is, we're going to get the same results out the other side. So just a really important fact that we need the network to obey. We utilize skip connections here. So then we keep our dimensionality of our vector equal to 22. And then through a series of 3 linear layers, we collapse that embedding down to a single dimension, which is the probability of each residue binding the antigen. One footnote, which I've kind of glossed over up until this point, is that we focus our efforts on the CDR loops plus 2 residues on either side only. And the reason that we do that is because if we consider the entire variable region, which other methods have done in the past, we found that the EGNN network was really quite unstable. There's a class imbalance of 10 to 1, and it was struggling to train properly. So what we can do is we can retain the vast majority of those residues and just focus our search on this much smaller area, and then simply extend our results at the end by predicting 0 for all other residues. And this is an approximation that holds really well because only about 1% of residues outside of this search area are actually found to bind the antigen. So this is what paragraph would look like working on a real complex. So here I've included the antigen just for context. So the antigen doesn't go into our network at all. Our network is antigen agnostic. We only include the antibody, but again, this is just for context here. And what we can see is this is the entire Fab region of the antibody. The binding is most often found in the FV or almost entirely within the FV. And again, mainly on the CDR loops at the end. The paratope is shown in red here. And those are our kind of ground truth labels, which we want to try and predict once we get to the other end of the network. So what we do is we take in this the structure, that could be a crystal structure or a model structure, and we represent that as our graph, really simple graph with the 22-dimensional feature vectors. We pass it through the 6 graph layers, the 3 linear layers, and it collapses it all. So we've got a probability of each residue binding the antigen. So the reason why I've included this as a kind of qualitative example here is that it shows one of the good things about paragraph, and that is that it seems to give more attention to the residues that are kind of more central to the binding of this protein, despite it not being exactly on the tip of the arm, which is kind of a more classical position for the antigen to be bound. But it also shows one of the limitations. So you can see that just outside the dotted gray circle on the left-hand figure, we do have a couple of residues which are found to bind, but because these lie out of our search area of the CDR plus or minus 2, then we do have to predict 0 for these. So there are some gains to be made, but there are inevitably some losses in this approximation. So that's the qualitative kind of power of paragraph. And now this is just showing how paragraph stacks up against some existing paratope prediction methods. So I won't go into these other methods in detail, but I will go into our baseline. So our baseline is super simple. We just look at the training set, our training set, and we look at every sequence position in our training set, and we look at the proportion of residues that are found to bind at each sequence position. We then just take our test sets, and again, we look at the sequence positions, and for every sequence position, for every antibody, we simply predict that proportion which was observed in our training sets. So very simple approximation, but it actually ends up being the best performing metric on the ROC AUC. And that is because this is a highly class imbalance problem, and this metric can be hacked in these instances. So what we want to do is pay attention to the area under the precision recall curve in these instances. One thing to note is that all of the results in white are evaluated on the same test sets and on model structures evaluated over the entire variable region. Pecan is the current state of the art, and that uses a graph convolutional network. It uses attention from the antigen, and it uses a more complex 62-dimensional feature vector. But what we see is that paragraph using equivariant graph neural networks and a simpler feature vector with no antigen information actually exceeds the performance of Pecan. Sorry. And promisingly, what we've done is we've compiled a larger expanded data set. So all of these other data sets, all of the white ones, use a data set that was compiled a few years ago. The growth of structural data has been quite large in that time. So we've now got 2.5 times as much data. So we've compiled this larger data set and we've tidied it up slightly after finding a couple of issues in the Pecan data set, which we can possibly look at later if there's time. This is the final slide before I conclude. And this is a really exciting part about how Paragraph works. And that is that the performance of Paragraph actually improves with the quality of the models that you feed it. So there are certain antibody modeling tools. So we used our blooper, and a blooper actually, every time it predicts a structure, predicts 5 different decoys for that model. And then by looking at the diversity amongst those decoys, we can actually get a confidence in our model. If they're really different models that are produced, the model is probably a little bit rubbish. If they're all really similar, then the model is going to be very good. And this decoy diversity has been shown to correlate very well with the true RMSD. So what we see here is that by taking only the top models, we actually get improved paratope prediction performance. And this is really great for right now because it can act as a proxy for paratope prediction accuracy. If we have good models, we probably have good paratope prediction. And it's also good looking to the future because as antibody structural modeling continues to improve, we'll continue to get improved paratope prediction performance for free. So just to recap, what we're seeing is that paratope prediction is really important for a couple of reasons. So antibody design, so that was maybe looking at improving binding affinity or improving the stability of the antibody. And for computational docking to reduce that combinatorial search space and get better docks faster. We've shown that Paragraph in the last couple of slides actually outperforms the current state of the art using modern equivariant graph neural networks, yet simple feature vectors and no antigen information. And then 3 key points that we've kind of compiled alongside this work is providing a simple baseline, which I think that not enough methods necessarily do this, but it's always good to have a very strong baseline to compare your method against. And also in looking in more detail at the data sets which previous methods have used, we've identified a couple of potential issues and therefore compiled a cleaner, larger data set, which is freely available on GitHub, and would encourage any future attempts to either use this or compiler, at least make use of the more data that's available now. And finally, and possibly most importantly, is we evaluate our method on model structures. And this is something that previous methods haven't necessarily given enough weight to. It's maybe been relegated to the SI. But this is a really important point because now we've got good models. We need these techniques to work well on model structures. And we've shown that Paragraph's performance continues to improve with model confidence. So all that's left to do is to thank my supervisors, Professor Charlotte Dean, and my industrial supervisors, Newton and Ian, and the rest of OPIG, where you can see the majority of them there. And thank you to you all for listening.
Thank you. Are there any questions? Hi, thanks for a great talk. I'm really interested in your baseline, and I recognize that is really important. Can you just tell me a bit about the difference between ROC and precision recall, and why, exactly why ROC is misleading in this case, but precision recall is the right thing to do?
Absolutely. So the class imbalance in this issue is around 10 to 1. So what we might be able to do is we might be able to get a very high true positive rate and a very low false positive rate. But because there's so many false positives, they just completely outweigh the true positives in this example. And this is why we need to look at that.
Okay, cool.
Thanks, Louis, for the great presentation. Have you systematically assessed how your model behaves when you leave similar structures out and how sensitive it is to small changes that might change a lot whether a residue is set to 1 or not?
So we haven't performed a systematic analysis like that, but what we do is we introduce a 95% sequence identity cutoff. So no structures in our data set in the original smaller Pecan data sets or in our expanded data set have more than 95% sequence identity.
Mm-hmm. And have you done anything regarding sensitivity to small changes?
No, apart from running on many random seeds, no, I'm afraid not.
Thank you.
Thank you.
Hi, this is really interesting, but I was wondering if you looked at your results in the context of CDR length, because with longer CDRs, you might get sort of folding in and like binding not to the antigen, but rather like sort of folding in on itself. So are you able to distinguish like residues that are actually binding to the antigen, and how does that vary with the length of CDR?
Very good point. So what we class as binding is a simple distance cutoff. So any heavy atom of the antibody, which is within 4.5 angstroms of a heavy atom of the antigen. So if the CDR-H3 folds in, it's still just going to be those that are in contact. In terms of looking at the correlation with H3 length, what we did look at was, unsurprisingly, model confidence is better for shorter CDR-H3s. So some of this improvement, we have looked into this, is undoubtedly due to shorter H3s, but nevertheless, we can still use the model confidence as a proxy for paratope prediction performance. So we still think it's somewhat useful, but definitely shorter H3s, easier to model, easier to predict the paratope of, I think.
Great, thanks.
Thank you.
Sorry, just one more.
Yes.
Just out of curiosity, what is the edge on your graph modeling?
It's
That.
a very simple, it's just an edge exists. We don't have any edge features, and they exist between residues that are separated by 10 angstroms or
10
less.
angstroms. That's quite long. How did you define that?
So we didn't actually play around with that, but what we did play around with was the number of graph layers. So how far do these messages propagate? And we found that 6 layers was enough for a residue on one side of the antibody to learn about everything that's happening on the other side, but not too many that it just kind of smooths everything out. But it would be interesting to play around with that parameter.
Cool.